Chapter 3. We've made it to Chapter 3. Topics in differentiation. We're going to talk about taking derivatives of unique functions in this chapter. And we're going to start the chapter out by talking about implicit differentiation. Now, what is implicit differentiation, you ask? And how is it different than the differentiation that we've been doing so far this year? Well, what we've been doing is called explicit differentiation. I give you something like y equals stuff, f of x equals stuff, or g of x equals stuff. And I just say take the derivative. Maybe I word it out as take the d dx or something like that. And so you find dy dx or f prime. Well, what if we're given an equation like this guy down here, where it's not y equals? For example, like a circle or an ellipse or a hyperbola. What do? Well, implicit differentiation allows you to take the derivative of a crazy function like that without having to solve for y first. So how do we do it? Well, it's a four-step process, really. First things first, don't change anything. Don't change your equation. Don't change it at all. Just take the d dx of both sides. You're literally going to write out d dx of both sides. That's step one. Differentiate both sides with respect to x. So if you're taking the derivative of something that is just an x, you're going to differentiate that normally. Okay, you just take the regular old derivative. However, if you take the derivative of something with an I attached, you take the y rather, a y attached, you're going to take the derivative of y like you normally would, but you're also going to attach a dy dx to it. So you're going to differentiate every term that you have in a crazy equation. Take the derivative of everything. The one thing that you have to remember is when you take the derivative of something with a y attached to it, you have to attach a dy dx to it. Now, you're going to have a bunch of terms floating around on each side of an equal sign, probably. You're going to take everything with a dy dx attached to it and move it to the left side of the equation. So if it's already on the left side, you're going to keep it there. If it's not, you're going to subtract it or add it to both sides, whatever you have to do. Anything that is not a dy dx that's on the left, you're going to move that to the right by adding it or subtract it. So everything on the left should be something dy dx plus something dy dx minus something dy dx. And everything on the right should be stuff without dy dx. So now, and this is step 3, that you have nothing but dy dx's on the left, factor out a dy dx. So what you should be looking at now is dy dx, parentheses, stuff, equals stuff. Step 4 is you take that parentheses and you divide it from both sides. So if you have dy dx times parentheses and you remove the parentheses, then all you have on the left is a dy dx. Which means you've just found your derivative. So chances are your answer is probably going to be some crazy looking fraction, and that's okay. Most of the time, not always. But that's implicit differentiation. Okay, you literally are now taking, and we could do implicit differentiation. I mean, it makes sense. The way we normally take explicit differentiation is if I give you y, we're finding dy dx. So if you d dx y, you get 1, and you attach a dy dx. So we're technically doing implicit differentiation when we take all other kinds of derivatives, but now we're going to make it more complicated. And Avril Lavigne always begs the question, why? Why'd you have to go and make things so complicated? I guess Avril, she has acne and she rocks harder than anybody in the office.
All right, so we're going to start out by doing exactly what we just described. We're going to use implicit differentiation to find dy dx given that equation right there. So Let me just rewrite it out. I've got y squared minus 3y plus 3x squared equals, and I'm going to leave myself a space on purpose, x plus 1. The first step in implicit differentiation is to differentiate both sides with respect to x. What that looks like is I take the ddx of both sides. Now you take turns taking the derivative of every term. Any term that has a y in it, you attach a dy dx. So the derivative of y squared is 2y. Since you took the derivative of a y, you're going to attach dy dx to it. Take the derivative of negative 3y. That's negative 3. Since you took the derivative of a y, you're going to attach a dy dx to it. The derivative of 3x squared is 6x. I'm not attaching a dy dx to it because I'm taking the derivative with respect to x. Even if I wasn't thinking, I would attach a dx dx to it, which is just 1. So you would multiply 1 to it, which changes absolutely nothing. That's going to equal the derivative of x with respect to x is 1. Don't attach anything. And the derivative of 1 is nothing, 0. Step 2 is anything that has a dy dx attached, keep it or move it to the left. If it doesn't have a dy dx attached, keep it or move it to the right. So that has a dy dx, I'm going to leave it on the left. That has a dy dx, I'm going to leave it on the left. That doesn't. So I'm going to subtract that from both sides and move it to the right. So that happens. Now I'm going to go to the right side of the equal sign. That has no attachments, so I'm going to keep it on the right. So now what I'm going to write out is 2y dy dx minus 3 dy dx equals 1 minus 6x. Now that I have nothing but dy dx is on the left side, I'm going to factor out a dy dx from everything on the left. When I factor a dy dx out from 2y, I'm left with 2y. And when I factor a dy dx out from negative 3, I have negative 3. The right side doesn't change. Now my goal is to find dy dx. So my last step is to divide both sides by the stuff that is not dy dx. So I'm going to divide both sides by 2y minus 3. I'm going to divide both sides by 2y minus 3. That crosses out. And my final answer is going to be dy dx equals 1 minus 6x over 2y minus 3. And more often than not, when we do these problems, we do end up with a fraction on the right side. And most likely, or more often than not, I guess I should say, we're going to have y as part of our answer on the right side. That's kind of the goal of implicit differentiation. You use implicit differentiation when you have more than just a y floating around in the original problem. And since we had a y squared, that complicates things, and we can't just simply, set everything equal to y and do what we normally would have done at the beginning of the year. All right, so let's do a few more, shall we? We have xy squared equals 1. So we're going to, let me rewrite it up here where I have a little bit more space, way up here. Xy squared equals, I'm going to leave myself some space, 1. I'm going to ddx both sides. Okay, which means differentiate with respect to x. Now, on the left, since I have xy squared, what I have to do is I have to apply the product rule. All right, so it's going to look like this. I'm going to let u equal the x, and I'm going to let v equal the y squared. When I take the derivative of x with respect to x, u prime is just going to be 1. When I take the derivative of v with respect, or which is y squared, with respect to x, v prime is going to be 2y. Good thing I use pencil. 2y dy dx. Remember, when you take the derivative with respect to x of something that's not x, you just take the derivative like normal and you attach the d whatever dx to it. So the derivative of xy squared with respect to x becomes u prime v plus v prime u. U prime v is 1. So this is the left side. 1 times y squared plus v prime u, which is going to be 2y dy dx, u, which is x. That's what this guy turns into. Boom, boom, boom. The derivative of 1 is nothing. So let me simplify this, clean it up, move to the top right a little bit. 1 times y squared is y squared plus 2, and I'm going to multiply the x. I'm going to include the x there. 2xy dy dx. And that's going to equal 0. Let's get rid of all the non-dy dx's. So I'm going to subtract y squared from both sides. Subtract y squared from both sides. That crosses out. I now have 2xy dy dx equals 0 minus y squared is just negative y squared. I only have one thing with the dy dx on the left, so I don't have to worry about factoring out the dy dx out of everything on the left because I only have one thing on the left. So what I can do now is just divide both sides by 2xy. And dy dx is going to equal, well, look what I have. I have 2 y's, or a y squared up top and a y on the bottom. So I can cancel out a y from each. And this leaves me with negative y over 2x. Okay. Let me rewrite out this guy up here where I have a little more space. X squared plus 2xy plus y squared equals, leave some space, 16. Let's ddx both sides. The derivative with respect to x of x squared is just 2x. This guy is a product rule problem, so I'm going to let u equal 2x, and I'm going to let v equal y. The derivative of 2x with respect to x is just 2. And the derivative of y with respect to x is 1 dy dx, or just dy dx. Okay, so let me give myself a little bit more space. I'm going to move that 2x down. Plus, and I'm going to put this in brackets just so I have the space. U prime v is going to be 2y plus v prime. Oh, okay, never mind. I'm good. I forgot to put the prime there. V prime, so dy dx, u is 2x. That's my product rule problem. The derivative with respect to y squared, or with respect to x of y squared, is going to be 2y dy dx. And the derivative of 16 is nothing. All right, so let's clean this up. These brackets aren't necessary anymore. I have 2x plus 2 times y plus 2x dy dx plus 2y dy dx equals 0. Let's remove all the non-dy dx's. So I'm going to subtract 2x and 2y. So I'm going to subtract 2x and 2y. I'm going to run out of room. That cancels out. That cancels out. 2x dy dx plus 2y dy dx is going to equal negative 2x minus 2y. I'm going to factor out a dy dx from the left. When I do that, I have 2x plus 2y. Oh, get out. Look at that. Scrap paper that I found on the ground. Well, from the trash can. I can now divide both sides by 2x plus 2y. That leaves me with dy dx equals negative 2x minus 2y over 2x plus 2y. Why don't I factor out a negative 2 out of the top and factor out a regular 2 out of the bottom? Or better yet, easier, I'll factor out a negative 1 out of the top. Dy dx. Factoring out a negative 1. When I do that, I'm just left with x plus y. Better yet, 2x plus 2y, because that wouldn't be correct, over 2x plus 2y. Oh, look. So after all of that, dy dx is just negative 1. So I'm going to do C up here. X cos y squared equals, leave some space, y cubed. I'm going to ddx both sides. I am forced to use product rule over here. So my u is going to be x. My v is going to be cos of y squared. U prime is 1. V prime is going to be chain rule. Take the derivative of the outside, which is negative sine keep the derivative, or keep the inside, so y squared, but multiply the whole thing by the derivative of the inside. What's the inside? Y squared. What's the derivative of y squared with respect to x? 2y dy dx. So the entire left side becomes u prime v, cos of y squared, plus v prime u. So plus negative sine, and I know it looks sloppy, but I'll fix it in a little bit, sine y squared times 2y dy dx. That's just the v prime times u, which is just x. That is going to equal So that's just the product rule. All of this is just what I did on the left side, just product rule stuff. All of that is going to equal the derivative of y cubed with respect to x. So 3y squared dy dx. All right, so let's clean this mess up right here. I have cos y squared. I'm putting in parentheses because it just looks nicer. What do I have? I have 2, I have y, I have x, and I have a negative. So minus 2 xy, right? 2xy negative sine of y squared dy dx equals 3y squared dy dx. Now, for the first time today, I have a dy dx on the right, so I need to move it to the left. So I'm going to subtract both sides by 3y squared dy dx, both sides by 3y squared dy dx. And while I'm at it, I have a non-dy dx floating around over here. So I'm going to subtract both sides by cos of y squared. So you cross out, you don't combine, but you're now on the same side. You cross out. So what we have so you're going negative 2xy, yeah, you can see, negative 2xy sine y squared dy dx minus 3y squared dy dx you're gone equals negative cos y squared. Let's factor out the dy dx. When I do that, I have negative 2 x y sine y squared minus 3 y squared equals negative cos y squared. And now divide both sides by negative 2xy sine y squared minus 3y squared, both sides. Gross. So you're gone. Ah! Well, I knocked over my document camera like a buffoon. But I only have to write out the answer, so let's do just that. You are now gone. And my final answer is dy dx equals negative cos y squared over negative 2xy sine y squared minus 3y squared. And there you have it. Awful, terrible problem. Let's hope that D is a little bit nicer. Let's hope. And let's hope I don't knock down my document camera again. Whew. All right. Can't make any promises, though. Tangent x plus y equals, leave a space, 16 plus y. The right side's going to be lovely, I feel. I'm going to ddx both sides. So I have chain rule. I'm going to take the derivative of the outside stuff, which is secant squared, keep the inside stuff, times the derivative of the inside stuff. You ready? I'm going to multiply this whole thing by the derivative of the inside stuff. The inside stuff is x plus y. The derivative of x is 1. The derivative of y is dy dx. Not so bad. That's going to equal the derivative of 16, which is nothing, plus the derivative of y, which is dy dx. So watch what I do. I'm going to take 1 and multiply to that, secant squared x plus y. And the reason why I'm doing that is I have that dy dx that I have to attach. So I have plus secant squared x plus y dy dx. That's going to equal nothing plus dy dx, so just dy dx. Let's get rid of u by subtracting it from both sides. So you're gone. And I need to move u to the left, so minus dy dx minus dy dx. So now on the left, what I have is secant squared x plus y dy dx minus dy dx equals negative secant squared x plus y. Let's factor out the dy dx. When I factor out the dy dx out of the first thing, I'm left with just secant squared x plus y. And when I remove a dy dx from negative dy dx, I'm left with negative 1. Divide both sides by secant squared x plus y minus 1. Cross that out. And my final answer, which I'm going to put on the left, is dy dx equals that. So dy dx equals negative secant squared x plus y over secant squared x plus y minus 1. Woo! So I have to find the slopes of the tangent lines to the curve y squared minus x plus 1 equals 0 at 2 specific points. So I have to do that guy and I have to do that guy. But before I can do either of them, I need to find the derivative of that equation up there. Well, what I could do is I could, add x, subtract 1, and square root both sides, positive or negative. But, we do have this nifty thing called implicit differentiation, which I'm going to use instead. So let me write out this equation one more time. Y squared minus x plus 1 equals, give some space, 0. And I'm going to ddx both sides. Remember, when you take the derivative of something, you are finding the slope of the tangent line at whatever point we need to use. So when I ddx y squared, that leaves me with 2y dy dx minus 1, because the derivative of negative x is negative 1, plus 0 equals the derivative of 0. So you're useless, so are you. So let's add 1 to both sides. And let's divide both sides by 2y. And so whatever shape that this is when it's graphed, the derivative is going to be that equation right there. Okay, no x's appear anywhere. So I'm going to, for this part, for 2 regular 2 negative 1, I'm going to plug 2 negative 1 into that equation right there. Well, that's my x and that's my y. I'm not going to plug in any x because I don't have an x there. So dy dx equals 1 over 2 times y, which is negative 1. So I get 1 over negative 2, or negative a half. So the slope of the tangent line at 2 negative 1 of that equation is going to be that guy. Ooh, for 2, 1, the slope of the tangent line at any point x is 1 over 2y. Well, I'm going to plug in the point 2, 1, which I have no 2 to plug into because I have no x. 1. 1 over 2 is 1 over 2. And that's the slope of the tangent line at that guy. Okay? Remember, slope of the tangent line is a derivative, or derivative is the slope of the tangent line. All right, we are going to use implicit differentiation to find, what does that mean? The derivative second time around, or the second derivative. I don't know why I had to word it the way I did that first time, but it is what it is. I'm going to do this way up here where I'm pretty sure I'm going to need all the space I can get. Y cubed minus x cubed equals, save some room, 27. And let's ddx both sides. The derivative of y cubed with respect to x is going to be 3y squared dy dx, because we're taking the derivative of a y with respect to x, minus the derivative of x cubed with respect to x is minus 3x squared. No attachments. Equals the derivative of a constant is nothing. So I have to get dy dx all by itself alone on the left. So let's add 3x squared, add 3x squared to both sides. 3y squared dy dx is now going to equal 3x squared. Is dy dx all by itself now? Nope. Let's divide both sides by 3y squared. Oh, look at that. When I divide that by 3y squared, that goes away. And look at these 3's. They go away too. God is good. So dy dx is equal to just x squared over y squared. That's not bad. So let me rewrite that out over here. I'm going to put a little box around it for no reason at all. Let me rewrite it out over here. dy dx equals, leave some space, x squared over y squared. Now I have to find the second derivative. So I'm going to ddx both sides. ddx both sides. On the left side, I get the second derivative of y with respect to x. On the right side, I have quotient rule. I'm going to let u equal x squared. I'm going to let v equal y squared. U prime is going to equal 2x. V prime is going to equal 2y dy dx. And v squared is y squared squared. Okay, so quotient rule is u prime v, so 2x times y squared minus v prime u, so 2y dy dx times x squared all over y to the fourth. A couple things before I tarry forward. That's 2xy squared, no big deal. Why do I have the derivative floating in there? That doesn't seem right. Oh, you know why? Because it's not right. I just found out that dy dx is x squared over y squared. So I'm going to write out 2y dy dx is x squared over y squared times x squared over y to the fourth. So that's 2x squared, y squared, I mean, minus 2. Technically I have, and I'll write it all out, y x to the fourth over y squared over y to the fourth. Which is 2 xy squared minus 2 x to the fourth over y. I can multiply the top and the bottom by 1 over y to the fourth sorry about my arm being in the way, and that's going to give me, that cancels out, 2x over y squared minus 2 x to the fourth over y to the fifth. Whew! I never said it would be easy. I just said it would be fun. Okay, that's that. That's the end of the section. Bye.